Welcome to the video lecture on Taylor and Maclaurin series. We can use the same process that we use to find a Taylor or Maclaurin polynomial to find a power series for a particular function as long as the function has infinitely many derivatives. The following theorem gives the form that every convergent power series must take. If a function f of x is represented by a power series of the form n equals 0 to infinity of a sub n times x minus c to the n for all x in an open interval I containing c, then these coefficients a sub n equal to the nth derivative evaluated at c divided by n factorial, so that our function f of x is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial x minus c squared, and so on. This is your basic Taylor polynomial. If we continue this up to infinity, then this gives us an infinite Taylor polynomial called a Taylor series. And this theorem is justified by basically repeating the process developed for a Taylor polynomial using an infinite number of terms. Now, the series obtained is called the Taylor series of the function f at c. If c is 0, then this is called a Maclaurin series for the function f of x. Now, one can always find a Taylor series for a function if the function has an infinite number of derivatives at c. We can also find the interval of convergence for the series obtained. In most cases, the series will converge to the function from which it was derived on its interval of convergence. However, sometimes the series will converge, but to a different function. As we develop power series for non-algebraic functions, it will be important to show that our series actually converges to the intended function. Two of the useful series obtained in the last section, in the last video lecture, are going to be the power series for the ln of 1 plus x over 1 minus x, which we derived to be 2 times the sum from 0 to infinity of x to the 2n plus 1 over 2n plus 1, and it converges for the absolute value of x less than 1, and the power series for the inverse tangent of x, which is the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1, which converges for the absolute value of x less than or equal to 1. Both were derived using integration and or substitution on the geometric series x to the n, which we already know has the sum 1 over 1 minus x. This comes from that formula a over 1 minus r. Now, since both of these came from a formula or a power series that we already knew converged, we know that both of these series not only converge, but they converge to the function which they represent. Most of the series we developed in the last section by recentering, substitution, integration, or differentiation started with a geometric series, so they will always converge to the function they represent, and any new series created from the geometric series will also converge to the intended function. Let's recall how to create one of these Maclaurin polynomials, and we're going to create a Maclaurin series and make it infinite. So let's do this for f of x equals to sine of x, and once we come up with our series, we're going to determine the interval of convergence. So in order to do this, we need to find all of those derivatives, because those are going to become the coefficients of our power series. So if we start with sine of x, then the first derivative is cosine of x, second derivative will be minus sine of x, and then this will be negative cosine x, back to sine of x, and then back to cosine x. If we plug in 0 into those, all the signs are going to go to 0, since sine of 0 is 0. So this will be 0, this will be 0, this will be 0. All those even powers are going to go to 0. All the odd powers are going to either be 1 or minus 1. Cosine of 0 is 1, negative cosine of 0 is negative 1, cosine of 0 is 1. So the Maclaurin series for sine of x is going to look like this very first term, which is just a 0, plus this first derivative divided by 1 factorial times x, plus the second derivative over 2 factorial times x squared, plus the third derivative divided by 3 factorial times x cubed, plus the fourth derivative over 4 factorial times x to the fourth, plus the fifth derivative over 5 factorial times x to the fifth, and so on. So what this is going to do for us is all of these even powers disappear, and we just get for sine of x that this is going to be an x, since 1 over 1 factorial is just a 1, and then we're going to get a minus x cubed over 3 factorial plus an x to the fifth over 5 factorial. Then we'd get an x to the seventh over 7 factorial that's negative, and so forth. If we generalize this using summation notation, notice that we want all of these odd powers and we want them to alternate. So we're going to need a negative 1 in there, and it starts with a positive. So if I let this power just be an n, then when n is 0, the very first term is going to be positive, and then the next term will be negative, and so forth. So this will give us the right signs. And in order to generate these odd powers, I'm going to take my x and I'm going to raise it to the expression 2n plus 1, which generates every single odd number starting from 1 on. So when n is 0 here, this will be 1. When n is 1, this will be 3. When n is 2, this will be 5, and so forth. In the denominator, we want that same odd number factorial. So this is called the Maclaurin series for the sine function, and it's definitely something that you would want to memorize because you will be using it quite often here. Now let's find the Maclaurin series for cosine of x by differentiating the power series for sine of x. So instead of going through this whole process up here again, which is very time consuming to calculate all of these derivatives, what we can do is just manipulate this sine of x Maclaurin series that we already know, and we know that the derivative of sine of x is cosine of x. So the derivative of its power series should be the power series for cosine of x as well. So the derivative of x goes to 1 minus, when I bring down the 3, it will cancel with the 3, but I'll be left with a 2 factorial in the bottom and an x squared on top. When I bring down the 5, it'll cancel with the 5 on the bottom, but I'll have a 4 factorial left and an x to the 4th on top, and then this will become minus x to the 6th over 6 factorial, and so forth. So it looks very similar to the sine series, but now we have all the even powers here. And if we generate this with a summation notation, this is going to alternate, so we want negative 1 to the n, since we want to start with a positive, and this time we want all these even powers, so I'm just going to let this be x to the 2n over 2n factorial. So when n is 0, we're just going to get 1. When n is 1, we're going to get 2's. When n is 2, we're going to get the 4's. When n is 3, we're going to get the 6's, and so forth. So this is the Maclaurin series for cosine of x. So memorize both of these. Finally, let's do the Maclaurin series for e to the x. Now what we want to recall about our function e to the x, the nice thing about it is that its derivative, is always e to the x as well. So that means when we plug in 0, which you want to do for a Maclaurin series, e to the 0 is always 1. So all of our coefficients of those derivatives in the numerator are all going to be 1's. So this e to the x is going to be the very first term, which is 1, plus 1 over 1 factorial times x to the first, which just reduces to an x, plus an x squared. The coefficient here would be a 1, and we're dividing this by 2 factorial. Then for the next term, we'd get an x to the 3 over 3 factorial, and again the coefficient on top would be a 1. And then we'd get an x to the 4th over 4 factorial, and the coefficient of the derivative would be a 1. So this is what our e to the x series looks like, written in summation notation. This is just an x to the n over an n factorial. So that's your third one that you want to have memorized as well. Now all of these can be easily shown to be convergent for all real numbers using the ratio test. However, the power series may or may not converge to the function from which they were derived. Okay, so the interval of convergence, using the ratio test, you can prove that these intervals of convergence are all real numbers for all three of these. So these always converge. So it's not always true, unfortunately, that a Taylor or Maclaurin series converges to the function from which it was derived. The last three were true. They do converge to the function from which it came from. But there could be functions which have the same derivatives at C but are different elsewhere. So remember that the coefficients of the power series are the values of the derivatives. So to get your power series, you just use the derivative evaluated at C. So it's possible that you could have a function that just so happens to match at C at all the derivatives. So it would have exactly the same coefficients as another function. For example, this function here. This function is -1 for all x's less than pi over 2, and then it looks like sine of x between -pi over 2 and pi over 2, and it's equal to 1 for x greater than pi over 2. The graph of this function looks kind of like this. It's -1 when we're less than pi over 2. This should be a negative right here. -pi over 2, and then it looks like the sine curve, and then it's +1 from pi over 2 on. So it looks like this shape right here. So this is obviously not exactly the same thing as the sine curve. It looks like the sine curve just between -pi over 2 and pi over 2, but everywhere else it's different. But if we're looking for the Maclaurin series, that means we're looking at the power series centered at 0. And that means at 0, all the derivatives of this particular function are going to be all the derivatives of the sine function, since that's the part of the function we use when we're looking at 0. That's this middle domain right here. So the Maclaurin series for this function will actually look exactly like the Maclaurin series for the sine function that we got up here. But that can't happen, right? Because you can have the same Maclaurin series as the sine function, but a series can't converge to two different functions. And what we want to make sure is that we want to be able to determine what the series we derived converges to. So we want to make sure that we're not converging to two different functions. So that's this theorem that we're going to talk about next. It's called the convergence of Taylor series. If a function f has derivatives of all orders in an open interval I centered at C, then this Taylor series right here converges to the function from which it was derived if and only if the limit as n goes to infinity of our remainder goes to 0 for every x in that interval I. So if a power series converges to f of x, then the series must be a Taylor series, even though it may have been obtained using some other method than Taylor's formula. However, every series formed using the Taylor series formula will not necessarily converge to f of x. For a very quick proof here, what we can show is that in a Taylor series, the nth partial sum is exactly the same as the nth Taylor polynomial. So s sub n of x is equal to our nth polynomial approximation using our Taylor polynomials. And since we know that this nth degree polynomial, p sub n of x, is equal to our function minus the remainder, then what we can say is that the limit as n goes to infinity of this nth partial sum is equal to, since these are equal, this is equal to the limit as n goes to infinity of our nth Taylor polynomial, which is equal to the limit of our function minus the remainder. And if we split that up, then this becomes the limit as n goes to infinity of f of x minus the limit as n goes to infinity of r sub n of x. And this is just f of x right here because it's not dependent on n at all. This is the true value of the function using all infinite number of terms. This one is only going to, if this one goes to 0, then that's the only way this nth partial sum is going to equal to our actual function. So we need this to go to 0 so that our limit of our nth partial sum just equals to the true value of the function. So for a given x, the Taylor series converges to the function if and only if that remainder goes to 0. So let's do an example here. Let's show that this series right here converges to sine of x. That is, we're going to show that the limit of the remainder goes to 0. Okay? So what we want to do here first is we want to use the Taylor series that we just came up with. We already derived a Taylor series for the sine of x function. So let's recall what we came up with. Sine of x was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And if we look at the general term here, the nth term would be negative 1 to the nth times x to the 2n plus 1 over 2n plus 1 factorial. So it would look just like this. And what we want to show is that this is true for all x. So we want to show that sine of x actually equals this infinite polynomial for all values of x. Okay, so we're going to look at that Lagrange remainder, which is this r sub n of x. And what it is for the Lagrange formula was the nth plus 1 derivative evaluated at some value z over n plus 1 factorial times x to the n plus 1. And we want to show that this remainder goes to 0 in the limit. So what would this nth plus 1 derivative look like? If you think about the sine function, if f of x is equal to sine of x, then what is the nth plus 1 derivative at any value z going to possibly be? Well, the only derivatives of sine are either positive sine, negative sine, positive cosine, or negative cosine, depending on what type of derivative you're looking at, the first, the second, the third, the fourth, or whatever. They only cycle through those 4 possible values. So the nth plus 1 derivative is either plus or minus sine of x, or plus or minus cosine of x. And if we're looking at this at z, then this is going to be plus or minus sine of z, or plus or minus cosine of z. Now, what do we know as a bound for that? Well, we know that sine and cosine are always less than or equal to 1 for every value of z. So that means, therefore, that this remainder, which is equal to this nth plus 1 derivative at z over n plus 1 factorial times x to the n plus 1, must be less than or equal to, if this is going to be less than or equal to 1, then that leaves us with just x to the n plus 1 over n plus 1 factorial. So the remainder is bounded by this term. So let's look at the limit of this remainder as n goes to infinity. So that means we need to look at the limit as n goes to infinity of this x to the n plus 1 over n plus 1 factorial. Now this x is like a constant. It could be 2 or 3 or 4. So this is like 2 raised to a variable. So that's exponential. And on the bottom we have a variable factorial. So that's a factorial. So this is like an exponential function over a factorial function. Now, in the previous video lecture on sequences, we talked about the growth rates of these two, and what we found was that factorials blow up faster than exponential functions. So as n gets really, really big, this factorial is going to get bigger faster and go to infinity faster than the top does. So that means that the bottom is going to go to infinity faster than the top, so the fraction as a whole is going to go to 0. So this limit of an exponential over a factorial goes to 0, which is what we wanted to show. We just showed that the remainder does go to 0. Therefore, our power series that we derived converges to sine of x. Okay? Let's try this again for the power series for e to the x. So this was the power series that we derived for e to the x. So what we want to look at to see if it's going to converge is that remainder term. So the remainder term, r sub n of x, we know is going to be equal to the nth plus 1 derivative evaluated at z times x to the n plus 1 over n plus 1 factorial. This is what the Lagrange remainder formula tells us. So what do we know about this nth plus 1 derivative if we're talking about the e to the x function? Well, the derivative of e to the x is always e to the x. So if we evaluate this at z, then this is going to be e to the z times x to the n plus 1 over n plus 1 factorial. That's true for every value of z. So what about this limit then? What is this limit going to do? The limit of the remainder then is going to be the limit of this expression right here. And e to the z is not a function of n, so we can pull that e to the z out front. It's not a function of n. It's kind of like a constant here. So we're pulling it out of our limit. And what we have again is this exponential. X is acting like a constant, being raised to a power that's continually getting bigger and bigger and bigger. And on the bottom, we have that factorial again. So the same argument that we had for the sine function, factorials get bigger faster than exponentials. So in this fraction, if this bottom is getting bigger faster, then the fraction as a whole is going to go to 0. So that means this remainder does go to 0. So our series, our Taylor series here, does converge to e to the x. So using the list of given power series as a start, let's create power series for each of the following. And why would you want to do this? Why wouldn't you just start from scratch and create the power series for this function? Well, if you were going to do this from scratch, you would start with your function f of x as sine of x squared. And to do a Taylor series or a Maclaurin series, you have to look at a derivative. So we would have to look at all of these derivatives. Now, taking one derivative of sine of x squared isn't too bad. That would just be cosine of x squared times the derivative of x squared, which is 2x. To take a second derivative, that's going to require a product rule. You would need 2x times the derivative of cosine, which is minus sine of x squared times another 2x, plus cosine of x squared times the derivative of 2x, which is 2. And immediately you can see that this is getting much messier than we want. So to find the third derivative and the fourth derivative would just get really, really time-consuming and tedious. So we want to avoid having to rederive all of these Taylor polynomials by looking at all these derivatives if we can. If we already have a power series for a function that looks close to this, it's easier to use the known power series and just make some substitutions to figure out what our power series should be. So that's what we're going to do here. We know that sine of x has as its power series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. You can write this using the power series notation if you prefer. That would be, let me make some room here, that would be equal to the sum from 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. So how do I get sine of x squared out of this? Well, just a basic substitution. Swap out all of these x's and put in an x squared instead. So this is going to become an x squared. X squared cubed, you multiply powers there, so this becomes x to the 6th over 3 factorial. X squared to the 5th, multiplying 2 times 5 gives me 10 over 5 factorial, minus x squared to the 7th becomes a 14 over 7 factorial. And in terms of our summation notation, we would swap out this x with an x squared. And if you multiply those two powers together, then this becomes negative 1 to the n x to the 4n plus 2 over 2n plus 1 factorial. So there's our power series for sine of x squared. Okay? So it's much quicker to just do a basic substitution on a power series that we already know than to try to recreate that Taylor series using all those derivatives, which for this function are going to get messy very fast. So let's use that same idea and see if we can come up with a power series for x times cosine of x. Well, we already know a power series for cosine. Its power series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. And in terms of its summation notation, that would be the sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So why not use this, and how could I manipulate it to get x cosine x? Well, just take this times x. So each of these is going to get an extra power of x added in. So this will become an x minus an x cubed over 2 factorial plus an x to the 5th over 4 factorial minus an x to the 7 over 6 factorial, etc. And over here, when I multiply by an extra x, if I take this times x, this is like an x to the first. So when I add those powers, this new power will be 2n plus 1 over 2n factorial. So we're getting the odd powers on top, but even denominators. So here's my power series. All right, how about a power series for hyperbolic cosine, or cosh of x? Well, to figure this one out, you need to go back and recall what the definition of hyperbolic cosine is. Hyperbolic cosine is defined to be e to the x plus e to the negative x, all divided by 2. And we can recall that e to the x has as its power series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. This is just the sum from 0 to infinity of x to the n over n factorial. So what would the power series of e to the negative x be? Well, I would just substitute in negative x's for all of these. So the ones that have even powers, when you plug in a negative x, that negative is going to disappear because of the even power. But the odd powers will keep the negative. So this is going to become 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. And in terms of the power series here, substituting in a negative x here, that's going to give you that alternating negative 1 out front, and the rest of the formula stays the same. So to get hyperbolic cosine, what I'm going to do is I'm going to take these two power series, add them together, and then I'm going to divide that by 2. So what I'm going to do with that division by 2, let's just call that a 1/2 out front. And let's go ahead and take the power series for e to the x, which is this 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And then I'm going to add to that this power series for e to the negative x. So 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, etc. So what's going to happen here? All of the odd terms will have opposite signs, and all of the even terms will double up. So this is going to be a 1/2. 1 plus 1 will be 2. We'll get 2 of these x squared over 2 factorials. We'll get 2 of the x to the 4th over 4 factorials. We'll get 2 of the x to the 6th over 6 factorials, etc. But all the odd ones cancel out. Now if I distribute my 1/2 across, I lose all those 2's. So this becomes 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, etc. And if you want to write that in summation notation, you can. This would just be x to the 2n over 2n factorial. So there's our power series for hyperbolic cosine. All right, how about the power series for e to the x minus 1 over x? Now remember, your option here could be to calculate all the derivatives, f of x, f prime of x, f double prime of x, and so forth, and then plug in 0, and then figure out your Maclaurin series from that. That's pretty time consuming. The other option is just to use the known series for e to the x. We know that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So this is just the sum of x to the n over n factorial. So what's going to happen if I subtract 1 from this? Well, the 1 cancels out. In terms of this notation over here, you're losing that n equals to 0 term. So you could rewrite this as the sum from 1 to infinity of x to the n over n factorial. We're losing that very first term. Now what happens if I divide that by x? So over here on the left side, we started with an e to the x, then I subtracted 1. So now what's going to happen if I divide this by x? Well, that means my power series for e to the x minus 1 over x is going to become, now I'm going to lose a degree of x, so this x over x becomes a 1. This x squared over x becomes an x over 2 factorial plus an x squared over 3 factorial, etc. And in terms of my power series over here, remember it's starting at 1 now, and when I divide x to the n by an x, this becomes an x to the n minus 1 over n factorial. And there's my power series. Okay, on the next example, we want to find the first 3 terms of a power series for f of x equals e to the x cosine x. So we already have a power series for e to the x. We already have a power series for cosine x. We wouldn't want to have to take derivatives of this because they are going to get very messy because of that product rule. So let's take advantage of the power series we already know. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. Now we only want the first 3 terms, so most likely that's going to be a constant, a first degree term, a second degree term, possibly a third degree or a fourth degree term if some of those earlier terms are missing. So when I do this product, I'm going to only look at the relevant terms. I'm not going to go all the way out in this infinite polynomial. So if I want e to the x cosine x, we're going to take this whole power series times cosine's whole power series. Now this would be impossible to do because it's infinite, but we only want the first 3 terms, so we only need to look at what is going to result when we multiply the first few terms by the first few terms. So that's what I'm going to do here. So we have to basically do some distributing. I'm going to take this 1 times this 1 times our negative x squared over 2 factorial, and this 1 times x to the 4th over 4. I'm guessing that my first 3 terms are not going to have a degree higher than x to the 4th, so that's why I'm not going to continue to keep distributing. So if I distribute my x times 1 will be x times a negative x squared over 2 factorial will be a negative x cubed over 2 factorial. And then an x times an x to the 4th over 4 factorial. This is probably too large, but I'll just put it in anyway. X to the 5th over 4 factorial. Now let's take our x squared over 2 factorial times 1. X squared times an x squared will be, this will be minus because of the minus sign, and we're going to get a minus x to the 4th over 2 factorial. And then let's do this one here is probably going to be too big, so I'm not going to bother. That would be an x to the 6th, so I think that's too big. And then we're also going to have, let me get another color in here so we can see through all these lines. We might need this x cubed over 3 factorial times 1. So that would be an x cubed over 3 factorial, and then probably this one will be too large, but I'll write it in just in case. An x cubed times an x squared will be a negative x to the 5th over 3 factorial 2 factorial. And all the remaining terms would have higher degrees, so most likely they're not going to be a part of these first 3 terms. So now we need to simplify. So if I look here and try to see what's going to happen, we've obviously got a 1 here, and then I'm going to look for any x terms, and the only x term I have is right here, so that'll be my second term. And then look at my x squared terms. I have a negative x squared over 2 factorial, and then I have a positive x squared over 2 factorial. So those actually end up canceling each other out. So that's kind of why I look ahead a little bit and look at these x cubed terms and potentially the x to the 4th terms, because sometimes some of these terms might cancel out and you'll need to look at the next higher term if you want the first 3 terms. So the squares are gone. So let's look at our cubes. We've got 1 here and 1 here, and that's like a negative 1/2 plus a 1/6. Negative 1/2 is the same as negative 3/6, plus 1/6 is negative 2/6, which reduces to negative 1/3. So the coefficient that I'm going to have for this x cubed term is a negative 1/3. And that's my first 3 terms, so I don't even need to look at my x to the 4th or x to the 5th. So there we go. Let's find a power series representation for sine of x over x, and then we're going to use it to find the limit as x goes to 0 of sine of x over x. So the power series for sine of x was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. All those odd powers. And if we divide this by x, we're going to lose some of our powers of x here. So we'll have sine of x over x equals 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial. So when we divide by x, we're going to lose a power of x everywhere. So we'll get x over x, which is 1, minus an x squared over 3 factorial plus an x to the 4th over 5 factorial minus an x to the 6th over 7 factorial, etc. And now all we want to do is take the limit of this as x goes to 0. So if we put a limit in front of all this, all of these terms with x's in them are all going to go to 0, so all we'll be left with is 1. And this is actually a limit that we proved earlier in Calc 1. And this is just an alternative proof that this limit equals to 1. Alright, on the next example, we want to verify that the sum from 1 to infinity of negative 1 to the n minus 1 times 1 over n factorial is equal to e minus 1 over e. And then we're going to use this series that we have right here to approximate the sum with an error less than 0.0001. So let's take a look at what some of these terms will look like. So here's my series. So when n is 1, this will go to 0, so we'll get a positive term, and 1 over 1 factorial is just a 1. When n is 2, this will now be odd, so we'll get a negative, and this will be 1 over 2 factorial. When n is 3, we'll get a positive again, and we'll get 1 over 3 factorial. So it's 1 over these factorials, and they're alternating in sign. So this is what that expands to. Now keep in mind, this should look vaguely familiar. It's kind of like our e to the x series, and you see some e's here, so that's kind of a hint. We know that e to the x is the sum from 0 to infinity of x to the n over n factorial. So that would just be 1 plus x squared over 2 factorial. sorry, my pen is being finicky today, plus x to the 3 over 3 factorial, and so forth. So e to the 1 then would be this series with 1 plugged in, which isn't quite the series that we have up here. E to the negative 1 would be this series with negative 1 plugged in, which would be 1 minus 1 plus negative 1 squared stays positive, negative 1 cubed stays negative, negative 1 to the 4th becomes positive, and so forth. And again, that's not quite the series up here that we're looking for. But if we take a look at this series right here, the 1's cancel out, and if you compare it to this series up here, it's got these terms the same but opposite signs. So if I threw a negative in front of it and a 1 in front of that and looked at 1 minus e to the negative 1, that would equal to the 1 from here minus all of these terms. And when you distribute that negative across, you get 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, etc. And that is this series up here. So 1 minus e to the negative 1 is equal to this series. Now think about what 1 minus e to the negative 1 equals. If you want to do a little bit of algebra on that, that's 1 minus 1 over e, and getting a common denominator, that's an e on the bottom, and this would be e over e is the same as 1 minus 1. So e minus 1 over e is equal to this series that we were given. So we've just proven the first part. We've just proven that e minus 1 over e does indeed equal this power series here. Now we want to use this series to approximate the sum with an error less than 0.0001. So if we want the error to be less than 0.001, then we need to find the first term that's going to be less than that. So we need the first term less than 0.0001. Now look at these generic terms up here. We're going to disregard the negative 1 because when we look at error, we look at the absolute value of it. So we're going to look at 1 over n factorial. This is our generic term. And we want to know when is that less than 0.0001. And you're just going to want to use your calculator here. If you take some reciprocals, this means we're looking for when is n factorial going to be greater than 1 over 0.0001, which is the same as 10,000. So what number, when you take the factorial of it, is bigger than 10,000? Well, that would be 8. 8 factorial is 40,320. So this will be true when n equals to 8. So keep in mind, that's your error term. So the sum that we want to use is actually going to be 1 less than that. So we can use up to n equals to 7 and ensure the correct accuracy. So what would the first 7 terms be up here? Well, we're going to do all of this. This was n equals to 1, 2, 3, 4, 5, 6, 7. So it's going to be all the way up until that 1 over 7 factorial. So that would be, with n equals to 7, that would look like 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial plus 1 over 7 factorial. And as a decimal, this is equal to 0.632148. And that's going to be our approximation of the sum. and we're guaranteed now to have an error less than 0.0001. So this is our approximation to e minus 1 over e, because that's what the value of our sum was that we proved earlier. Okay? All right, on the next example, we want to use a power series to approximate this integral from 0.5 to 1 of cosine square root of x dx with an error less than 0.00001. Now, this is going to be impossible to do using just normal antiderivatives. There is no known antiderivative of cosine square root of x. And you can try all different kinds of integration techniques, but there's not going to be anything out there that's going to be successful. So to actually compute this definite integral would normally be impossible. But what we're going to do instead is we're going to change this cosine squared of x into its power series. Basically, it becomes an infinite polynomial. And we do know how to integrate polynomials. There are antiderivatives of those. So all we have to do is find out what that polynomial is going to be, integrate it, and then we're going to plug in our bounds. So let's start with the power series for cosine x. We know that that's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. And as a summation notation, that's the sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So what would cosine of square root of x look like? Well, we're just going to substitute in a square root of x for all these x's. So square root of x squared just becomes an x. Square root of x to the 4th just becomes an x squared. Square root of x to the 6th becomes an x cubed, and so forth. So this power series becomes negative 1 to the n, and when I do square root of x to the 2n, this square root of x is like an x to the 1/2, and when I raise that to the 2n and multiply these two powers together, the 1/2 and the 2 cancel out, so we're just going to get an x to the n over 2n factorial. So there's the power series for cosine square root of x. So now what I want to do is integrate this, so I'm going to integrate the power series instead. So what would that look like? Well, the integral of 1 would just go to x. The integral of x becomes an x squared over 2 times that 2 factorial. The integral of x squared becomes x cubed over 3 times 4 factorial. The integral of x cubed is x to the 4th over 4 times 6 factorial, etc. And in terms of this summation notation, this would be negative 1 to the n, and I'm adding 1 to the power, so this becomes an n plus 1 over that n plus 1 times our 2n factorial. Now what we'd want to do, since this is a definite integral and it has bounds, we want to plug in our bounds into this infinite series. Unfortunately, we can't plug in 1 into an infinite number of terms and plug in 0.5 into an infinite number of terms. That would just be impossible. So this is where our approximation comes into play. We need to know how many terms should we use to approximate this polynomial. How far out do I need to go so that when I do plug in 1 and I do plug in 0.5, the error that's going to be incurred is less than 0.00001. Well, that requires looking at that generic term and finding out when that term is going to be less than our error. So the generic term is right here. So we're going to look at x to the n plus 1 over n plus 1 times 2n factorial, and we want that to be less than 0.0001 for both of these bounds, x equals 1 and x equals 0.5. Now think about that for a moment. If you plug in 1 and you plug in 0.5, which one is going to give you a greater error? This is going to be its largest, when x is its largest. So this is going to be as big as it can be when x is 1, and it'll be smaller than that when x is 0.5. So just to save on the amount of work here, I'm only going to look at the x equals to 1 because it's going to give me a larger error than the x equals 0.5 would, since 0.5 is smaller than 1. So we only need to look at what happens when x is 1. So let's plug in 1 here, and 1 to the n plus 1 is just going to stay 1. So this becomes 1 over n plus 1 times 2n factorial less than 0.0001. Now you want to look on your calculator for that. You would type in this expression on the left side into your y1, and then look at a table and see for what value of n does this y value become smaller than 0.00001. And it happens when n equals to 4. This is equal to 0.000005, which is smaller than that error. So since n equals to 4 is what makes this true, then that means we can use up to n equals 3 for our polynomial. So we want to go back to our series, which was up here. And instead of doing all infinite number of terms, we're just going to go up to n equals to 3. So from 0 to 3. And that will give us the desired accuracy. Whoops, I'm looking in the wrong one, sorry. What I want to be looking at is right here. This was the result of the integration. So negative 1 to the n, x to the n plus 1 over n plus 1 times 2n factorial. That's the power series that we got after integrating. And we're only going to look at these for n equals 0 to 3. So let's expand this out for those 4 different n values. So when n is 0, we're going to get 0 plus 1, which is 1, times 0 factorial, which is 1. So all of this just goes to an x. When n is 1, we're odd here, so this will be minus, and we'll get an x squared on top, and we'll get a 2 on the bottom times a 2 times 1, or 2 factorial on the bottom. When n is 2, we're back to being positive again, and we're going to get an x cubed on top, and we're going to get a 2 plus 1, or 3, times a 2 times 2, or 4 factorial. And finally, when n is 3, we're back to being minus, and this is going to be an x to the 4th over 4 times 6 factorial. So this was n equals 0, n equals 1, n equals 2, n equals 3. Now what do we want to do with this? We've just found out that that's as far as I need to go in my infinite series to get the desired accuracy. So now that I know where I can stop, now we can plug in our bounds, and our bounds are 0.5 up to 1. So if I plug in 1, this is going to look like 1 minus 1 over 2 times 2 factorial plus 1 over 3 times 4 factorial minus 1 over 4 times 6 factorial. And then we want to subtract from that this same expression with a 0.5 plugged in. So 0.5 minus 0.5 squared over 2 times 2 factorial plus 0.5 cubed over 3 times 4 factorial minus 0.5 to the 4th over 4 times 6 factorial. And you can punch all of that into your calculator, and you're going to get 0.324327. So there is our approximation to that definite integral with an error less than 0.00001. Now if you use the function integrate command on your calculator to compute this particular integral, what function integrate will tell you for an answer is that this is 0.324332. So we're pretty close to that. And function integrate uses a similar process that we're doing here to be able to get values for these definite integrals that we wouldn't normally be able to integrate because we can't find an antiderivative. All right, next example. Now consider the Maclaurin series for sine of x, cosine of x, and e to the x. These converge for all x's, but they converge slowly for values of x away from the center point of 0. So let's talk about how to find a Taylor series for f of x equals to e to the x centered at 1. So what we're going to have to do here is recreate our series using that process for finding Taylor polynomials. So that means we're going to have to start with our function, and we're going to have to look at all of its derivatives, which for e to the x isn't too bad. They're all going to equal to e to the x back again. So this would just continue on. And this time we're looking at a center point of 1, so we want to plug in 1 into these values in these derivatives. So e to the first is just e. So all of these derivatives are just going to equal to e. Now remember, these derivative values become your coefficients in your Taylor series. So to find our Taylor series, we're just going to use each of these derivatives as our coefficients, and we want to keep in mind that we're centering this at 1. So our very first term is just going to be what f of 1 is, which was e in this case. And then our second term is going to be this first derivative, that's your coefficient, times an x minus 1 over 1 factorial. Plus, your next term will be that coefficient e again, times an x minus 1 squared over 2 factorial. And then the next one would be that coefficient e times x minus 1 cubed over 3 factorial, etc. If you want, you can factor out that e from all of these and make this 1 plus x minus 1 plus x minus 1 squared over 2 factorial plus x minus 1 cubed over 3 factorial, etc. And in terms of summation notation, this would just be an e times the sum from 0 to infinity of that x minus 1 to the n over n factorial. So there's our Taylor series for e to the x centered at 1. Now let's find the Taylor series for 3 to the x centered at 2. So we're going to do the same exact process. You're going to start with your function, which is 3 to the x, and then you're going to start looking at its derivatives. So the derivative of 3 to the x is 3 to the x back again times the ln of 3, because we don't have a base of e here. So the second derivative will be the derivative of 3 to the x, which is 3 to the x, times another ln of 3 times the ln of 3 that we already had. So this is like 3 to the x times ln of 3 squared. So the third derivative, if you begin to see the pattern here, would be that 3 to the x back again, but now we're going to get an ln of 3 cubed. So we want to know what each of these values is centered at 2, so we have to plug in 2 for each of these x's. So if we plug in 2 into our function, 3 to the second is just 9. If I plug in 2 here, 3 to the second is 9 ln of 3, and then 3 to the second is going to be 9 ln of 3 squared, and then 9 ln of 3 cubed. So our Taylor series, centered at 2, is going to be this very first term 9 plus this first derivative, that's your coefficient, times x minus 2 to the first over 1 factorial, plus your second derivative times x minus 2 squared over 2 factorial, plus your third derivative times x minus 2 cubed over 3 factorial, etc. If you want to pull out the 9, you certainly can. So 1 plus ln of 3 times x minus 2 plus ln of 3 squared times x minus 2 squared over 2 factorial, etc. And in summation notation, this would be 9 times the sum from 0 to infinity of ln of 3 to the n, x minus 2 to the n over n factorial. Alright, what we're going to finish up with here is something called a binomial series. A binomial series is a series used to represent a function in the form of 1 plus x to the k. So it's taking something and raising it to an integer power, and it's useful for computing roots. And we'll see an example of this in a little bit. So if you look at f of x equals to 1 plus x to the k, if we want to derive a Maclaurin series for that, we're going to need to look at its derivatives and then plug in 0 for each of those since we're looking for a Maclaurin series. So here's our function. One derivative would bring down the k and subtract 1 from the power. Two derivatives, we would bring down the k minus 1 and subtract 1 from the power. Third derivative, bring down the k minus 2, subtract 1 from the power, and so forth. So if we plug in 0, 1 plus 0 is just going to be 1 to the k, or just 1. If we plug in 0 into this, we're going to get that 1 plus 0 again, which is 1, times k, so this will be k. If we plug in 0, this part goes to 1, and we're left with the k times the k minus 1. And over here, this part will go to 1, and we'll be left with k times k minus 1 times k minus 2. Now notice that if we went all the way to the nth derivative, for the third derivative we used k minus 1, and k minus 2. So this number right here is 1 less than the derivative that we were looking for. So if we want the nth derivative, we're going to have k minus 1, k minus 2, all the way down to k minus 1 less than this number. So that's going to be 1 less than n. And if you clean that up just a little bit, that's k times k minus 1 times k minus 2, all the way down to k minus n plus 1. Okay, so those are your coefficients. And just to note here, this product turns out to be k factorial, which would be k all the way down to 1. But notice I'm not going all the way down to 1. I'm stopping at k minus n plus 1. So what we can do is we can divide this by k minus n factorial, and that's all the terms lower here that we're losing, that we don't have in this product. So this k factorial over k minus n factorial simplifies into, k minus 1 all the way down to 1. And this is k minus n times k minus n minus 1 all the way down to 1. So you lose part of these, and the ones that you're left with are all the ones above k minus n, which is this k minus n plus 1 and above. So that's why this product right here is the same as k factorial over k minus n factorial. So what does this look like if we put it all together? So the series for 1 plus x to the k, the Maclaurin series, is going to be this very first term 1 plus this coefficient k. We're centering at x, so I'm just going to have an x here divided by 1 factorial, plus this coefficient k times k minus 1 times x squared over 2 factorial, plus k times k minus 1 times k minus 2 times x cubed over 3 factorial, etc. And the nth term here would be this k factorial over k minus n factorial, that's this product right here, times an x to the n over n factorial. And then this series would go on forever. And this value right here, k factorial over k minus n factorial times n factorial, is actually called a combination. If you've ever taken any kind of probability and you've talked about combinations and permutations, this is the formula for a combination. Okay? How many groups can you arrange? All right? So it can be shown using the ratio test that the radius convergence of this series is 1, and that the limit of that remainder does go to 0. So this series does converge to 1 plus x to the k for all x's less than 1 in absolute value. So we can use this infinite series here to represent 1 plus x to the k. So how does this help us? Well, we can use it to write Maclaurin series for more complicated looking functions. Now this function right here would have some pretty nasty derivatives if you had to start taking derivatives of this and deriving the Maclaurin series from scratch. So what we're going to try to do here instead is see if we can turn this into something that looks like 1 plus x to the k. And then we're going to use the power series for this manipulated. Alright, so somehow we need to take square root of 4 plus x squared and make it have this kind of a form to it. So I need to get a 1 in there, and right now I have a 4. So what I'm going to do first is I'm going to factor out the 4. Now when I do that, that means I'm going to have an x squared over 4 here, so that when I redistribute, the 4's would cancel, giving me back the original x squared that I had. Now the square root of 4 is just a 2, and 1 plus x squared over 4 under a square root is like a 1/2 power. So I am sort of rewriting this in this binomial form. So here was the formula we just generated on the last example. The power series for a binomial, 1 plus x to the k, is 1 plus k times x plus k times k minus 1 over 2 factorial times x squared plus k times k minus 1 times k minus 2 over 3 factorial times x cubed, and so forth. So now what we want to do is come up with the power series for 2 times 1 plus x squared over 4 raised to the 1/2. So we need a 2 out front times our infinite power series. And how do these compare? Well, instead of using x, I'm going to be using x squareds over 4 here, here, and here. And instead of using k, my k is going to be 1/2. So this would become 1 from this one plus k, and my k is going to be 1/2. And instead of x, this is my x. So I'm going to use x squared over 4 plus k again, which again is 1/2, times k minus 1. Well, 1/2 minus 1 is negative 1/2, all over 2 factorial, and this x is getting replaced with x squared over 4, and we want to square that. Plus, let's try one more. This k again is 1/2. K minus 1, or 1/2 minus 1, is negative 1/2, and 1/2 minus 2 is going to be negative 3/2. Divide that by 3 factorial, and this x gets replaced with an x squared over 4, and we want to cube that. So this is tedious and messy too, but it's still going to be a lot easier to do this manipulation than to try and take all these different derivatives of your function, plug in 0, and then try to figure out what your Maclaurin series is from that. So let's see if we can simplify here a little bit. Inside my brackets, I'm going to get an x squared over a 2 times a 4. Now I'm going to leave it 2 times 4 for now. We can simplify a little bit more in just a bit, but I'm going to eventually want to distribute this 2, so it'll be easier for me to just cancel out the 2's if I leave it like that. Now for this next term over here, we're going to get an x squared squared, so that's going to give me an x to the 4th, and it's actually going to be minus because of this minus that I have. So this plus actually turns into a minus, and I'm going to get an x to the 4th. I'm going to get a 4 squared from that 4 in the bottom. I'm going to get a 2 factorial, and a 2 times a 2 is a 2 squared. And all of those join the denominator. Then for my next term, I've got 2 minuses, which become plus. An x squared cubed becomes an x to the 6th. I'm going to get a 4 cubed. I'm going to get a 3 factorial, and a 2, and a 2 is a 2 cubed. And then I also have that 3 on top. Okay? So now I can go ahead and distribute my 2 across. So 2 times 1 is 2, plus this 2 will cancel with that 2, giving me x squared over 4, minus this 2 will cancel with one of these 2's, giving me x to the 4th over 2 times 2 factorial times 4 squared, plus I'll get a 3 x to the 6th over this 2 will cancel with one of these, so I'll have a 2 squared times 3 factorial and a 4 cubed, etc. And there's my power series. You can simplify more if you like. You can find out what some of those denominators would be. 4 squared is 16. 16 times 4 would be 64. So this could be an x to the 4th over 64 plus an x squared over 4 plus that 2 out front. And then this one over here would be a little bit messier to figure out. So I'll just put dot 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 for that. All right. So here's our power series for that square root of 4 plus x squared. All right. Next example. Calculate square root of 26 using a third degree polynomial. So I mentioned earlier that this binomial theorem is useful for calculating roots, and this is going to be an instance of that. So if you've ever wondered how does your calculator calculate the square root of 26, this is one way that it could do that. So what we're going to do is we're going to think of square root of 26 as this sort of binomial theorem. And we know that our binomial theorem is 1 plus x in parentheses to the k. And in this case, since I want a square root, I'm going to think of this as 1 plus x to the 1/2. I'm going to let my power k be that square root, or that 1/2 power. So what would 1 plus x to the 1/2 look like using that binomial expansion that we came up with? Well, the first term was 1, and then the next term was k times x. So our k is a half. So this would be a half times x. And then the next term is our k, again, times our k minus 1. 1/2 minus 1 is negative 1/2. And then this was an x squared over a 2 factorial. And then our next term is that k again, times k minus 1, times k minus 2. So that 1/2, negative 1/2, negative 3/2, and then this was x cubed over 3 factorial, etc. So if we clean that up a little bit, this is going to look like 1 plus a half x plus, this is going to be an x squared. It's going to be minus because we have that single minus sign, and we'll have a 2 squared from these two 2's and a 2 factorial. The next term will be back to positive because we have 2 minus signs. We'll get an x cubed and a 3 on top, and then we'll get 3 2's, or 2 cubed, and a 3 factorial in the bottom. Now, how does this help me with square root of 26? Well, what you want to do is you want to think of square root of 26 as 1 plus something. 26 is 1 plus 25. And 25 is a nice perfect square. You want to pick this number to be a nice perfect square if you can. So that means what we're going to do for our function is we're going to use the function f of x equals square root of x plus 25. And we're going to plug in x equals to 1. Once we get the power series for this function, we can just plug in 1 in for that x, and that'll give us an approximation to the value of the square root of 26. Now, I can't quite do this yet until I turn it into our proper form. So what we're going to do first is we're going to change some things around. So first of all, let me write this as 25 plus x under that radical, just because our binomial form typically has that x coming second. We don't want that 25 in there, we actually want a 1. So the first thing I'm going to do is factor out a 25. That'll leave me with a 1 plus x over 25. Square root of 25 becomes 5, and 1 plus x over 25 is being raised to the 1/2 power. So this is now our new binomial expression or binomial function. If we can come up with a power series for this using this formula up here, then if we plug in x equals to 1, then that will give me the square root of 1 plus 25, which is the square root of 26. So the power series will give me an approximation to the value of the square root of 26. So what we're really finding here is the square root of x plus 25, otherwise known in this more creative form as 5 times x over 25 to the 1/2. We'll have the following power series using this notation up here. First of all, we need to multiply everything by 5. And then instead of using x's up here, our x is actually x over 25. So we're going to substitute that in here, here, and here. So this becomes 1 plus 1/2 times, instead of x, x over 25, minus, instead of x squared, it's going to be x over 25 squared over that 2 squared and that 2 factorial, plus 3 times x over 25 cubed over 2 cubed times 3 factorial, etc. Now, to save myself some writing, I'm not going to bother to clean this up too much yet. What we want to know is that this is equal to square root of 26 when x equals to 1. So what I'm going to do is I'm going to plug in x equals to 1 into this power series. And that should give me an approximation to what the square root of 26 equals. So it's got to equal 5 times 1 plus 1/2 times 1 over 25, we're using x equals to 1, minus 1 over 25 squared over 2 squared times 2 factorial, plus 3 times 1 over 25 cubed over 2 cubed times 3 factorial, etc. Now we could go on here forever, but this particular problem told us to just use a third degree polynomial. So it's actually telling us when we get to stop. So we're going to stop after this cubic term. So I'm actually going to take this dot 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 out and just compute this. So on your calculator, it's messy, but you can do it. You're just going to type in 1 plus 1/2 times 1/25 minus 1/25 squared over 4 times 2 is 8, and so forth, and then multiply all of that by 5. So you punch all of this into your calculator, and what you're going to get is 5.09902. So that's our approximation to the square root of 26. The true value of the square root of 26 is actually 5.09901. So these are very close. Just by using a third degree polynomial, we were pretty accurate. Okay? All right, so if you want to know the square root of a value that's close to a nice perfect square, then you can create a function that looks like that perfect square plus x, and then recreate its power series using that binomial expansion. And then plug in however far away you are from that perfect square, use that value for x, punch it in your calculator for however many terms you want to go out to, and that's your approximation. All right, finally our last example here. We want to find a series for the inverse sine of x by integrating the series for 1 over the square root of 1 minus x squared. So what I want you to recognize here is that 1 over the square root of 1 minus x squared, if we rewrite that, that's the same as 1 minus x squared raised to the negative 1/2. Which is exactly like our binomial expansion. We want this to look like 1 plus x to the k. And I have a minus in there, so what I can do is make this a double negative and make this become plus a negative x squared, like that. I'm actually not using a double negative, I'm just going to attach the negative to the x squared and put that plus in there. So this becomes my 1, they match. Instead of using x, I'm going to use negative x squared, and my k is going to be negative 1/2. So first of all, let's recall what the binomial expansion power series is. 1 plus x to the k is 1 plus kx plus k times k minus 1 x squared over 2 factorial plus k times k minus 1 times k minus 2 x cubed over 3 factorial, etc. So what we want to do now is manipulate this and turn it into the power series for 1 over square root of 1 minus x squared, also known as this series right here. So 1 plus negative x squared raised to the negative 1/2. That would become this formula using negative 1/2 for the k's and using negative x squareds for the x's. So this 1 would stay 1. This k becomes a negative 1/2 since that's this power up here. And this x becomes whatever we have right here, which is our negative x squared. Plus k again, so negative 1/2. Negative 1/2 minus 1 would be negative 3/2. Instead of x, I'm using negative x squared, and I need to square that over 2 factorial. And let's do one more term here. K is negative 1/2. K minus 1 is negative 3/2. K minus 2 is negative 5/2. Instead of x, I'm using negative x squared to the third over 3 factorial. And then this would continue. Alright, so now we know the power series for 1 over square root of 1 minus x squared, because that's what this really is. This is 1 over square root of 1 minus x squared. So how does that help me get the power series for the inverse sine? Well, 1 over square root of 1 minus x squared is the derivative of the inverse sine function. So if I integrate 1 over 1 minus x squared under a square root, that integral is the inverse sine function. So all I have to do is integrate this power series. And that's going to give me, there's no bounds here, so there's going to be a plus c, and then this is going to become the integral of 1, which just becomes an x. We're going to get a minus and a minus, which becomes a plus, a 1/2, and this x squared becomes an x cubed over 3. We have a minus and a minus, which becomes a plus. This negative gets squared, so it's going to go away. And this is ultimately right here an x to the 4th. So when I integrate that, it's going to become an x to the 5th over 5. I have a 2 factorial. I have a 3 on top and a 2 squared on the bottom as well. Let's do one more term. We've got a minus, and a minus, which would stay minus, and this negative is getting cubed. So we're going to have a negative from there as well. So that's 4 minus signs, so it's actually going to become plus. We're going to have a 3 and a 5 from the top. We're going to get a 2 cubed and a 3 factorial on the bottom. And this is ultimately an x to the 6th, so when you integrate it, it becomes x to the 7th over 7. Now we have this c in there, so let's find out what c is by using an x value. We know that at 0, inverse sine of 0 is equal to 0. And if I plug in 0 onto this right side, all of these terms go to 0 except for the c. So that forces c to be 0. So that means our power series for the inverse sine of x is going to be just this x plus x cubed over 2 times 3 plus 3 times x to the 5th over 2 squared times 2 factorial times 5 plus 3 times 5 times x to the 7th over 2 cubed times 3 factorial times 7, and so forth. And you can actually put this into summation notation if you look carefully at the pattern here. On the top, you would need an x raised to those odd powers, so 2n plus 1. And on the bottom, you also have that 2n plus 1 from right here, here, and here. And then in the bottom, what this turns out to be is a 2 to the n to get these powers of 2's and an n factorial. And we actually want to square that and multiply on top by a 2n factorial. And it's tricky to see this, but if you plug in your 0 and your 1 and your 2, you'll see that it does actually generate these terms. Now, I think that that's kind of difficult to come up with that summation notation. So for me personally, I would accept you writing out your final answer this way. But it is possible, looking very carefully at the power, to come up with the power series expansion written in summation notation. All right, this is a tricky topic here, so be careful. This concludes our video lecture on Taylor and Maclaurin series. Good luck!